Hello, everybody. It's Mrs. Pound, and we are starting a new chapter, Chapter 14, on solutions from BJU Chemistry's 5th edition. We're going to first talk about section 14.1. Now, I have split this into two different videos, so an A and a B video. So today we're going to take a look at 14.1a, the dissolving process. Our objectives for the video are to describe the parts of a solution, categorize examples of solutions, explain why certain solutes do not dissolve in certain solutions, and compare unsaturated, saturated, and supersaturated solutions. So the first thing we need to do is talk about what a solution is. And we have talked about this in a little bit in a previous chapter when we talked about mixtures. So remember, a solution is a homogeneous mixture. That means if we take a look at these test tubes, it looks the same throughout and it is evenly distributed. Let's say there's food coloring in these tubes and water. We cannot see where there's food coloring particles and where there are water particles. It just looks the same throughout. Remember, homo means same. There are two parts to a solution. The first part is the solute, and this is the dissolved substance present in the smaller amount. In the background, I have a picture of sea salt. And as far as solutions are concerned, salt is a common solute that we have in solution. So commonly, salt is a solute. Now, remember, solutes cannot be filtered out of solution. So if we have salt water mixed together, they will go through the filter together. Solutes do not settle out of solution. That would be a precipitate. So solutes, like I said, stay the same. If there's any solute at the bottom, it's because we have a saturated solution, which I will be talking about later. Solutions are uniform. That means they're the same throughout. When we wear uniforms to work, we wear them so that everybody looks the same. Solutions are not chemically combined. So we have this looks like it's Epsom salts that were dissolved in water. We can evaporate that water and get the salt back. They did not change into a new substance. Solutions can also vary in their concentrations. So if we look at these different glasses, we can see that this solution is more concentrated because it's darker than this solution over here. And we'll talk about measuring concentrations later in this chapter. Now, if one liquid is soluble in another and can form a solution, the two liquids are said to be miscible. So think mixable, okay? And an example is alcohol and water. Miscible is only if one liquid is soluble in another and can form a solution, the two liquids are said to be miscible. And that sounds like mixable, okay? And alcohol and water are an example. This only works for liquid. And if we look in the background at the label, it says 91% isopropyl alcohol. That means that's 91% alcohol, 9% water is mixed in with it. And when you look at rubbing alcohol, you cannot see the difference between the two. So they are miscible, they are mixable, and they are both liquids. Liquids that separate after mixing are immiscible, and an example is oil and water. So in the background here, the water is up here, the yellower part is the oil. They are immixable. They are not mixable. That's where that word comes from. And so they will separate, like in your salad dressing. That's why you have to shake Italian dressing. So, types of solutions. You can have a liquid-liquid solution like rubbing alcohol and water that we already talked about. And remember, if they are miscible, and that only applies to liquids. You can have a solid solution, and we call those metal alloys usually, are the ones that come to mind here. And an example is brass, which is a mixture of copper and zinc. There are others like bronze and even our gold that we wear as jewelry are alloys. You can have a solid liquid solution. And an example is gold and mercury, which was a solution that was used for gold mining to purify gold. Also, when we have a mercury solution like this, it's amalgam, and that's what used to also be used for fillings. There was a mixture with mercury used to fill teeth. Solid gas mixture. An example is palladium and hydrogen. Hydrogen would be dissolved in palladium to purify the hydrogen, and it would be mixed with the metal, and then it would be extracted, heated and extracted from the metal. And then there are gas solutions like air, the air all around us. Now, as far as gases are concerned, gases can be solutes with the other phases of matter, the other states, but it cannot be the solvent. If it is, we have a colloid, something like clouds. So clouds are in air. Air would be normally the solvent, but it cannot dissolve the water particles because they're just too big. Because remember, gases are really spread out. So those water particles are just too big to really dissolve. And that's also why clouds are white, because they scatter light and colloids scatter light. So you can have a gas dissolving another gas, but a gas cannot dissolve a liquid or a solid. So the next topic I want to talk about is solubility, and this is the maximum amount of a solute that can dissolve in a specific solvent under specific conditions such as temperature and pressure. And I say that because as you raise the temperature, more or less of something will dissolve, and also pressure affects how a gas dissolves. This is typically reported as massive solute that will dissolve in 100 milliliters of solvent. This will be important when we take a look at solubility curves in the next video. A general rule for solubility is like dissolves like. And when I'm talking about this, I'm talking about polar and nonpolar solvents and solutes. So polar dissolves polar, nonpolar dissolves nonpolar. Polar solvents like water will also, some of them will dissolve ionic compounds as well. So polar, water is very polar, will dissolve polar or even some ionic substances. Nonpolar solvents like oil will dissolve nonpolar solutes. Something like if you get pine pitch on your hands, you can dissolve that actually with oil and get that off of your hands. Also, crystalline substances with high lattice energies that dissociation cannot overcome are insoluble. Dissociation is the breaking up basically of an ionic substance when it dissolves, but sometimes that energy to break up those crystals is just too high. They just want to stick together too much, and so they are insoluble. That's where we get our precipitates from. So you might remember when we talked about types of reactions, I had reacted sodium phosphate with copper 2 chloride. I had reacted these two things, and they say 0.05 molar. We're going to learn what that means. That has to do with concentration in this chapter. And when we reacted those, we got copper 2 phosphate. Copper 2 phosphate. And that was a precipitate. This is insoluble because its lattice energy is too high to break up the salt crystals in this. So let's talk about our last topic, and that is solution equilibria. And when we talk about this, there are three types of solutions we're going to talk about. The first is an unsaturated solution. This means the solution holds less than the maximum amount of solute that it could at the current conditions. For example, the solubility of potassium chloride at 60 degrees Celsius is 45 grams per 100 milliliters. So that's that solubility I talked about, reported in mass per 100 milliliters. But the solution only contains 25 grams of KCl in 100 milliliters of water. Therefore, we say it is unsaturated. Because it could hold 20 more grams, it's unsaturated because it could hold more. A saturated solution means that the solution holds the maximum amount of solute at the current conditions. So in the previous example, the water now holds 45 grams of KCl. It is saturated. It holds as much as it can at 60 degrees Celsius. And we also say that this solution is in dynamic equilibrium. What that means is that you can see we know it's saturated because there are crystals down here. Okay, that it doesn't mean that they're insoluble. What is happening is you get a saturated solution basically by adding just a little bit more after they all dissolve. And what's happening is those crystals down here, some of them are dissociating and dissolving, and some of them are coming out of solution and depositing on these crystals down here. So it is in dynamic equilibrium, and that solution up above in the water is saturated. Then we have supersaturated solutions, and actually this crystallization that you see in the background came from a supersaturated solution. This is the solution holds more than the maximum amount of solute at the current conditions. So the above water holds perhaps 60 grams of KCl, or actually it held it. What happens to get a supersaturated solution is you heat it up higher than the temperature that we were looking at. I believe it was 60 degrees Celsius. You heat it up higher so that more goes into solution, because at a higher temperature, more will be in solution. Then you cool it gradually, and it becomes super saturated. Then when it cools to 60 degrees Celsius, if everything's still dissolved, it's super saturated. At that point, you can do something like drop a seed crystal in there, and then you get all of this beautiful crystallization. You just drop a little crystal in there and it will come out of solution because it was super saturated, and then it becomes saturated. So our objectives were to describe the parts of a solution, categorize examples of solutions, explain why certain solutes do not dissolve in certain solvents, and compare unsaturated, saturated, and supersaturated solutions. There will be another video, 14.1b, for the rest of this section in your textbook.